Hi all, welcome to the Global Lecture Hall for the second lecture of this year ShanghAI lectures. Today, needless to say, we have a tight schedule. First, after this very short introduction, Rolf will give us, so we'll continue the main thread, giving us some insights on the limitation of what is named as the good old-fashioned AI from our perspective, and the benefits of an embodied approach to intelligence. Then around 10 after 10, we will have a short coffee break. Then just after the coffee break, we will have the first two of our guest lectures. The first one will be by Josh Bongard on the evolution of morphology. So we see a lot of morphological difference in our world, and we will see how this can be in some way modeled and simulated. And then we will, at around 10:50, we will have a lecture from Pedro Lima from the Instituto Superior Técnico de Lisboa about an interesting approach to collective robotics, which actually mimic the emergence of institutions in the human society. And finally, we will have a wrap-up. Just a couple of technical remarks. You can interact. You are strongly advised to interact, because this is one of the benefits of the way we are actually organizing this global virtual hall. And you can do, if you are in one of the rooms which are connected by video conference, you can do it by raising the hand, and maybe someone in the room send a small message, a short message by chat to Nathan, so that we can identify you. And then if you are following the streaming, or in any case, you can use the question board. I have here in the slide, there is the address, but you also find it in the lectures page of the website, or by Facebook through the ShanghAI lecture page, or through Twitter. There are a couple of Twitter hashtags which are dedicated to the lecture. And so this is the number 2. So after the introduction, in the first one, we will now go a bit deeper to see the benefits, pros and cons, and motivation for an embodied approach to intelligence. Then, so welcome again. And I don't know if I needed to introduce Rolf to this audience, or in general. So as you may know, Rolf is the director of Artificial Intelligence Lab. Is named sometimes Mr. Embodiment for the great work which he has done on the ideas, and also some interesting practical example of embodied intelligence. Is the inventor of the ShanghAI lectures. So he actually started the ShanghAI lecture in Shanghai several years ago, as we said before. Is the main author of How the Body Shapes Our Mind, Our Thoughts. And I think that the most relevant thing about Rolf is that he is really a crazy man. So I now pass the floor to Rolf. Welcome, and we are looking forward to your talk.
How can I? Here.
Yeah.
Share my screen. Desktop share. And oh, there is an echo here, huh? Okay. Can you see the slides?
Yes.
So, okay, well, there's an echo.
Yes.
I don't know what to do about that. So, let me also welcome you all to the Global Virtual Lecture Hall, to the Shanghai Lectures. I think many of you I already know, and I'm very happy to see all these sites connected to today from China, from Russia, from Japan, from Poland, and from Germany. And by the way, for those, I have a guest in the video conference here, Professor Verena Hafner from the Humboldt University in Berlin. They're also connected,
Verena.
I think.
I can see my students are all there. Hello.
They are there.
I'm glad it worked out.
Okay. Very good. So welcome. And I'm doing this video conference today from the University of Sussex. So there is a very exciting conference here of the EU COG network that's maybe interesting for some of you. That's a network for cognitive systems research. And the topic this time, topic area, I think is a very important and exciting one, is social and ethical aspects of cognitive systems. And this is the reason basically why I'm at the University of Sussex, and I'm very grateful that we have as a host the University of Sussex. For those who are not very strong in geography, here is a list. So this is the UK, and you can see Brighton, and the University of Sussex is very near Brighton, a little village called Farmwood. So that's where we're broadcasting from today. Okay, so now the topic is cognition as computation successes and failures, and I will argue why we need an embodied approach. Last week's topics were intelligence, and I think Fabio talked about the difficulties in defining intelligence, coming up with necessary and sufficient conditions. And I think the better question, rather than asking whether something is intelligent or not, the better question is, here's a behavior that we're interested in, and let's figure out how it works, how it comes about. I think I move over here a little. Okay. You also talked about measuring intelligence, IQ, and all the issues involved. Fabio introduced the Turing test and the Chinese room experiment. You remember, you have this room, then Chinese characters are handed in. Then there's a person sitting in the room, typically Searle, the philosopher who came up with this thought experiment. And then there is a set of rules, and what Searle does, takes the characters, matches them against a set of rules, comes up with an answer, and hands out the characters through the other window. And his point is that even though Searle does not understand a word of Chinese, the people that hand in the characters and get them out the other window get the impression that the Chinese room understands. And so his point is that just looking at input-output is not sufficient. And then you introduce the methodology of artificial intelligence, the synthetic methodology, understanding by building. Okay, that was last week. Now this week we look at approaches to intelligence, successes and failures, the need for an embodied approach, and the famous frame of reference problem. Okay, so let me start with the classical approach. It all started in 1956 at a conference in the US, in Dartmouth. There were a number of really seminal papers presented at this conference. So one of them was George Miller, eminent psychologist, and he gave a paper called The Magical Number 7 plus or minus 2. Now, some of you may have heard, I think if you're in psychology, you may have heard of this paper. What he was trying to do is to quantify the capacity of short-term memory. Now, it turns out that it's very hard to do in terms of bits. I mean, computer scientists try to quantify information content in terms of bits and bytes. It's very hard to do for short-term memory. There is a huge variation. So he suggested that rather than having bits to quantify the capacity, we use chunks. So, for example, you have a phone number, an international phone number, then you would divide it up into chunks. One for the international access code, the country code, the area code, and then the actual phone number, which makes it much, much easier to remember. But you cannot really say what the bits are. And then he suggested that the number of chunks that we can keep in short-term memory is roughly 7, but it's very vaguely 7. Could be 5, could be 9, something like that. Very famous paper. Second paper there was by Newell and Simon, two of the founding fathers of artificial intelligence, and they presented a program called the Logic Theorist, which could actually prove theorems in propositional calculus, the very simple, or sentence logic, very simple calculus. And then Herbert Simon said, modest as he was, he said, well, this is the first time in the history of mankind that we have a thinking machine. So basically at the time they were convinced if you have a computer program that can actually make proofs in first order, not in first order, in propositional logic, then you have a thinking machine. As we know by now, this was grossly overstated. The third seminal paper was by Noam Chomsky, a linguist, famous linguist, called Syntactic Structures, and it's probably one of the most quoted papers in linguistics. So he was trying to characterize language in terms of syntactic rules, which then turned out to be somewhat misleading, as we may see later on during the ShanghAI lectures. Another person who participated there, he was actually the initiator, was John McCarthy, a computer scientist, one of the really founding fathers of artificial intelligence. And that's where these were all computational approaches to intelligence, viewing intelligence as computation. Okay, there is something called functionalism and the physical systems hypothesis, which underlies a lot of artificial intelligence research. Now, the idea is that what matters is really, let's say, the symbolic level. The symbol level, the way this symbol level is implemented physically is actually irrelevant in this view, in this functionalist view. So this can be a biological brain, it can be electronic as in a laptop computer, it can be mechanical as in an abacus, or as the American philosopher Hilary Putnam put it, it could be Swiss cheese, which of course is a great pleasure for Swiss who are very fond of cheese. So basically a physical symbol system could be implemented in the form of Swiss cheese. Now, to go a little deeper here, functionalism and the physical symbol systems hypothesis. So roughly what the whole thing is about the models of the real world and representation. So we have in the upper half, we have the real world situation. We have blocks A, B, we have a table, and then we have a hand that moves the block B on the table. And in the lower half, we have a representation. We have block A, block B, a table. And we have the relations on B, A, and on A is on the table. And then we have a move operator, which corresponds to the T above, to the hand. And then we have a resulting situation. And then we have these encode. So it says like these arrows, encode, and then we have decode. Now the problem here is, this is a very obvious thing. It's the standard model relationship that you have. I think the real problem with this is that the here it says encode, and it seems very obvious, but in there you have the whole perceptual system. So it's far from trivial. So it's not as easy as it looks here. Okay, this approach to intelligence is also called GoFi. Does anyone know what GoFi means? From the Global Lecture Hall, GoFi. It's by John Hogland. Would anyone volunteer? GoFi, so that's the basically computational classical approach. Well, good old-fashioned artificial intelligence, as the philosopher John Hogland created or coined the term here. Now, the research areas that people were pursuing in this computational approach, or are still pursuing in this computational approach, is abstract problem solving, knowledge representation, reasoning, acting logically, and so on and so forth. I adapted this from a very nice book by Russell Norvig, Artificial Intelligence, a Modern Approach, which is about the classical computational approach to intelligence. Okay, let me now come to some of the failures and successes of the classical approach. You take a search engine. I'm not going to ask who knows Google. You take a search engine like Google, then there will be many algorithms. You will be using many algorithms that have their origin in this classical approach, like machine learning, on pattern matching, on heuristic search, and so on. Very successful story. Formal games, chess. I'll come back to that in just a second. Text processing systems, data mining systems. Of course, big data is a very successful story. Then appliances and manufacturing. And in a sense, these programs, if you look at them, are indistinguishable from computer applications in general. I think they're just very clever algorithms. And for that, they're also extremely useful. Here is just the example of chess in 1997, when actually the IBM's Deep Blue computer won against the world champion at the time, Garry Kasparov. He won an entire tournament. Or it, I should say it, not he. Okay, now what are the failures? It's more to do with things that are easy for humans. They turned out to be difficult for computers. So it's recognizing a face in a crowd, vision, perception in the real world, common sense, movement, manipulating object. This has turned out to be very difficult to handle with this classical approach. Now, a question to the audience, the global audience: why is perception hard? Originally, people thought that perception, well, all you need is a camera, and then you need a pattern matching system that matches what you see in the camera to a particular pattern. So basically you need a database of these patterns, you need a pattern matching thing, a camera, and then you have a perceptual system. Now, this didn't work at all. Now, why is perception in the real world so hard? Would anyone venture a hypothesis here? Anyone? If I, for example, if you look at this pen, right? Now, if I hold the pen, let's say I hold the pen like this, then the stimulation on the retina is very different from holding the pen like that. If I hold the pen like this, then the sensory stimulation on the retina is completely different, but it's still one and the same pen. And this seems to be something which is very easy to do for us, but very hard for computer programs. We continuously move in the real world. So the stimulation on the retina of the same object changes dramatically, and there is virtually no similarity between the two. So a simple pattern matching mechanism will not work for this. And we will see that perception is actually a highly sensory motor process rather than just input that is mapped onto some kind of internal representation. Okay, now let's look at some problems of the classical approach. I think the problems have their origin in anything that is to do with the interaction with the real world. And it is important to understand that there are some fundamental differences between real and virtual worlds. And as an example, we take here chess and real world soccer. So chess is a virtual, formal world. By the way, on the left, you see a former master student in our laboratory, Monika Seps. She's also a chess master, so one of the best chess players in Switzerland. Now, let's talk a bit about the virtual, formal world versus the real world. So, if you look at the game of chess, that's a virtual or abstract game. What does that mean? Or a formal game. So, on the one hand, you have board positions. Now, a board position is either a board position or not. I mean, it's purely digital, or as we would also say, symbolic. There is no sort of, it's a little bit this board position and a little this board position, but it's either the board position or not. And given a particular board position, then there is a finite number of moves, and all a player can do is select one of the moves from this list, from this finite list. And it's basically all. And in addition, if none of the players does anything, doesn't make a move, or if none of the players makes a move, nothing happens. By contrast, if you look at the real world, a game like soccer, basically you can do anything. You can sit down, you can jump up in the air, you can start singing a song. So there are an infinite number of things that you can potentially do. It's not that there is a limited set, a finite set of actions from which you can choose. Also, if you don't do anything as a player, then things will still happen, even if you don't do anything. In addition, you have physical sensors. We have our, visual sensors, but also if you take cameras, artificial sensors, there is always noise and there is always malfunction. That's the real world. Information acquisition in the real world takes time, and you only always have a very tiny fraction of the information available about the real world. So there is always a high level of uncertainty. In the game of chess, you have complete information. You know everything there is to be known about the situation. Okay? So we do have these fundamental differences. And in the real world, also we have very rapid changes that we have to adapt to. Okay. So this, I already talked about this. This is just a bit of a summary of examples of fundamental differences. If you look at the real world, information acquisition takes time. Even if it's very fast electronically, it still does take time because it is a physical process. And because of all these limitations that we have in the real world, Herbert Simon, as you can see in the lower part, coined the term of bounded rationality. So he said, because of these limitations, decisions that we are taking in the real world will always be of bounded rationality. Okay? So here is kind of a summary of the successes and failures. So on the left, the successes, applications, typically where applications are concerned. Chess, also manufacturing, a very important successful application area of the classical approach. The failures are more in the, of course, the classical approach contributed to our understanding of natural forms of intelligence, but I think it's limited. So foundations of behavior, I think we need a different approach. More natural forms of intelligence like perception in the real world, manipulation of objects, movement in the real world, anything to do with the interaction with the real world. And so if we compare an industrial environment to a real world environment, here we have, we take industrial robots. We have strong, precise, fast motors. So basically you tell a motor, if you have an industrial arm, you tell a motor to go to a particular position, it will go there. We have centralized control, we have a lot of computing power, we can use optimization. Also, what we should mention in addition, we have high predictability. So in essence, we can pre-program everything down to the last detail. Okay? By contrast, if you look at the real world, humans, we have low precision, compliant means that it's not like hard like an industrial arm, but if you encounter an object, the arm will yield elastically rather than push harder. It's reactive. We have to react to rapid changes in the environment, and we have to cope with high levels of uncertainty. Now, I know that many of you already think about the coffee break. If you sit now in your chair, you have no way of anticipating or planning the steps that you will be taking during the coffee break. But you will just go there, and then you will react to changes in the environment. So there is no direct transfer of methods, and I think we will talk later on about this transfer of method in a later lecture. If you just take the methods that work very well in an industrial setting, which is highly predictable, highly programmable, you transfer them to the real world, it's not going to work. Okay, now for the remaining about 5 or 10 minutes, I would like to talk about some of the fundamental problems of the classical approach, which are the symbol grounding problem, frame problem, and homunculus problem. So let me just start with this one. So the symbol grounding problem, a very fundamental problem. We can use symbols. We can talk about a house, which is a symbol. Now, the important question is, what is the connection between the symbol house and the real world? Right? Fundamental question. Imagine that you're using, let's say you want to take a train, let's say from Shanghai to Beijing. So you're sitting in front of a computer and you're looking at the schedule. The program, which is the schedule and that will give you this information, knows nothing whatsoever about the meaning of a train. It doesn't know what departure times are. It doesn't know what tickets are. It has absolutely no connection in that sense to the real world. The whole connection is made by yourself. You are looking at these pixels on the screen and you are trying to make sense of it. So basically the grounding of these symbols is done by the human being. Now the problem is, because we're interested in robotics, how would you make this connection? How would you establish this connection in a robot? And that's a big question. Here is a nice, what you see on the slide is a very beautiful illustration by Gary Larson. Gary Larson has been thinking a lot about cognitive science and tries to illustrate these issues. The real world doesn't come with labels. So basically, he's trying to solve the problem by attaching labels to, shirt, house, door. But basically what you're getting is just a constantly changing stream of sensory stimulation. I think this is one of the fundamental problems which is very difficult to resolve with the classical computational approach. Now, going back to this notion of representation, we have the frame problem. Now, what is the frame problem? It's essentially about maintaining a model of the real world. So as before, we have this table and then we have the representation. If you want to maintain a model of the real world, you have to continuously monitoring what's changing. And then also you have to know what changes are irrelevant to the current situation. For example, there are a lot of, now I'm sitting in Brighton, downtown, there are a lot of cars moving, thousands of people, going to work right now. It's completely irrelevant to what's happening here. I don't need to track all that to maintain the video conference here. Now, there is an American philosopher that we will encounter, I think, many times, philosophy of mind, and he has a very nice illustration of the frame problem with a robot. Let me just go through this quickly. I think I still have time for this. So here's the text. Let me just read the text. I think it's beautiful. It's beautiful, so I think I want to take the original text by Daniel Dennett. Once upon a time, there was a robot named R1 by its creators. Its only task was to fend for itself. One day, its designers arranged for it to learn that its spare battery, its precious energy supply, was locked in a room with a time bomb set to go off soon. R1 located the room and the key to the door and formulated a plan to rescue its battery. There was a wagon in the room. I mean, this is basically here. There's kind of, you can see in the lower right corner, the wagon in the room with the time bomb and the battery. There was a wagon in the room, and R1 hypothesized that a certain action, which it called pull-out wagon room, would result in the battery removed from the room. Straight away, it acted and did succeed in getting the battery out of the room before the bomb went off. Unfortunately, however, the bomb was also on the wagon. R1 knew that the bomb was on the wagon in the room, but didn't realize that pulling the wagon would bring the bomb out along with the battery. Poor R1 had missed that obvious implication of its planned act. Okay, back to the drawing board. The solution is obvious, said the designers. Our next robot must be made to recognize not just the intended implications of its acts, but also the implications about their side effects. They called their next model the robot deducer, R1D1. I mean, those of you who know Star Wars, of course, they know what he's alluding to. They placed R1D1 in much the same situation that R1 had succumbed to. And as it too hit upon the idea of pull-out wagon room, it began as designed to consider the implications of such a course of action. It had just finished deducing that pulling the wagon out of the room would not change the color of the room's walls. That would have been completely irrelevant. And was embarking on a proof of the further implication that pulling the wagon out would cause its wheels to turn more revolutions than there were wheels on the wagon when the bomb exploded. Okay, next and last, back to the drawing board. We must teach it the difference between relevant implications and irrelevant implications, said the designers, and teach it to ignore the irrelevant ones. So they developed a method of tagging implications as either relevant or irrelevant to the project at hand and installed the method in their next model called R2D1. When they subjected R2D1 to the test, they were surprised to see it sitting Hamlet-like outside the room containing the ticking bomb. Do something, they yelled. I am, it retorted. I'm busily ignoring some thousands of implications I have determined to be irrelevant. Just as soon as I find an irrelevant implication, I put it on the list of those that I must ignore. And the bomb went off. So you can see the point. If you have a system that decides what's irrelevant by testing everything, then it's not going to work. So summary of these points, it's what's obvious to humans who have experience with the real world is not obvious to robots that have to use these representations. There are a vast number of potential side effects that are almost all of them will be irrelevant. So if we want to have a distinction between relevant and irrelevant in this approach, we must test them all. Okay, so this is not going to work. So I think we need an embodied approach. So the last 2 or 3 minutes, if I still have them, Fabio, if it's okay, I do the last 3 minutes. Yeah? The need for an embodied approach. So as I mentioned, there are different views of intelligence. The classical one, cognition as computation, cognition as an umbrella term for mental activities, for memory, problem solving, doing theorems, language, and so on. And there is the embodied approach, cognition as emergent from sensory motor and interaction processes. Okay. We had failures of the classical approach, which we already looked at. We have some fundamental problems of the classical approach, and we have Wolpert's quote. So let's look at that. Danny Wolpert, famous biologist from the UK, asked the questions, why do plants not have brains? I don't know whether you also asked yourselves the question, why do plants not have brains? And then he says, well, the answer is actually quite simple. They don't have to move. So, of course, plants do move. They move passively in the wind. They can turn towards the sunlight. But they don't have that spectrum of movements that we have as humans. So in this view, this gives us a nice, let's say, evolutionary perspective. So what we now call cognition or intelligence or the brain has evolved always as part of a complete organism that had to interact with the environment and survive and reproduce in this environment. So there is no algorithmic ether, but there is always a complete physical organism. And having a body is the only way in which we can actually communicate with the environment. So we need to understand that. Right. And so we always have the interaction with the environment, which is mediated by the body, and we always have the brain or the neural system, which is part of a complete organism. Okay, let me now just finish the presentation with the frame of reference problem, and I would like to show now the video by Haider and Simmel. Nathan, can you play the Haider and Simmel video? So it was, just watch it, and then we can have a short discussion. It's 60 years old by now. Okay. Okay, thank you very much. So would someone want to briefly comment on this? Just, I mean, what we saw basically. Anyone would like to comment? What did we see? How about the Humboldt University? Or let's see, we have Northwestern. Anyone? Ah, okay. Humboldt University, yes, go ahead.
We saw a fight between different triangles. This was like a room show, and yeah, the two triangles discussed and fight for the ball.
So I didn't quite understand that. So what can you say that maybe again?
Yeah, we saw like triangles fighting.
Yes, right. They were fighting, right?
Yeah.
Yes, and so basically, you know, the small triangle and the circle, you know, they are a couple, and you know, the other one is jealous, and you know, so we basically make up a story, even though we only see triangles and circles, right?
Mm-hmm.
So it's all in our heads. It's not in the triangles and the circles. So that's the frame of reference problem. And because the time has already advanced, I have a couple of slides on the frame of reference problem, but maybe Fabio can go through these slides next week, right? So then I think I will probably stop here and hand the floor back to Fabio. Okay, thank you very much for your attention. And I will stop sharing. Okay. Okay.
Okay, so I don't know if you have some question from the global hall. Maybe not. So we can now have, I think, about 5 minutes break. So we can start at 10:20. So we are slightly delayed, but I think it was worth. So see you in 5 minutes at 10:20 Central European time. Thank you all. See you later. I may just, but I need to. We may have also a little bit of a discussion. This could be a great way to transform a problem in an opportunity. So I think that what Rolf said is actually he gave some more detail that I did.
Right. So yeah, let's use this time for some discussion. If anyone has any questions or inputs.
Oh, because I was now trying to recover to recover some slide, but I think that we had some. So while in the first inaugural lecture, I actually raised some question and I tried to confuse the received opinion of intelligence. I think that today Rolf went really deeper in trying to argument, of course, in the time of less than an hour, why it's not so chess players don't solve the problem of intelligence, no? And he actually pointed out that while I mean, he didn't do. We will see it again, no? But just to improvise. So if you think now, if you think how the robot, I think you don't see me, so. No. So the difference, we will discuss this, no? The difference between working like a robot and working like a person, right? So it's really different. No? And this actually comes from the problem that Rolf pointed out. So the problem that if you actually think in terms of an abstract machine like the Turing machines. You have tape, you have a program to write on the tape and to delete symbol on the tape. We know that this, in principle, allows you to compute all the possible functions that you can compute. Is this enough? No? Also the example of coding, of decoding. Right? So the basic idea that we have about coding and decoding is that I have some kind of, for instance, now the idea, which is, I mean, is not such a strange idea, no? Because if you think how a typical computer vision system is currently organized, you typically will have a camera or two cameras or a time-of-flight camera, so some sensor device giving you a matrix of points, and then you have you send this to a computer, like that many times is really a laptop or something very similar to a laptop, and this data that you transfer are elaborated, and what you do, because I mean, the example from, you remember the example, no? How I know that this is a board, I write here board. Why this is a desk, I write here desk. And why this is Fabio, I write here Fabio. If you think about, in many, for instance, industrial application, is exactly what you do. You put an RFID tag. So, as soon as you have set the frame, we are able to do this kind of reasoning. No? So I say, so this is Fabio, and if you, I think that some of you at least have some experience with perception or artificial vision system. Well, typically, they work very well if I have a red ball and a green ball, and the computer knows that it has to choose between the green ball and the red ball. If there is a brown ball, you may already see many systems fall. But I mean, of course, the example that Rolf did from Dennett work, because I mean, you may think that philosophers are useless to engineers or to physicists. Not, but my favorite quote on this is to say that usually when an engineer tells you, especially engineers tell this, no? I'm not interested in philosophy. It really means that they follow 19th century positivists, right? So they have certain mindset. So they don't put into discussion the assumptions. And many times are the assumptions which mislead you. So this problem of a frame of reference, which actually also this year there will be the Swiss chocolates present for people noticing if by chance one day we don't quote the frame of reference problem, is really the basis, and for people like one of the main arguments in favor of an embodied approach to cognition is this one, because think again, because you may not notice this aspect, no? Because when you write the example of a computer vision, I think it's very suitable to this discussion, no? Because typically, if you think those of you who already had the opportunity to try to do some computer vision, no? Maybe a master thesis or a bachelor thesis or whatever, or if you are a PhD student, it's very likely that you have this kind of experience. What you typically do is this. You have this stream of 1,000 by 1,000 pixels, maybe you have colors, no? Or degrees of gray, and you have to understand that there is a chair there. And now, unfortunately, I have no visual support, no? But there are many different chairs. If you look into the screens, you can see this, that in one of the universities there are green or blue chair. Then there are other kind of more traditional desks in other place. Here we have red chairs. So the kind of a typical approach to this problem is very similar to the example of Dennett, because I say, okay, a chair has 4 legs, and it is more or less this high. So if in my stream of, or in my 1,000 by 1,000 matrix of 1,000 by 1,000 matrix, I have a concentration where I can see the chair, this picture. I do a comparison. If the two pictures are close, that's a chair, okay. But the chair can be rotated, or the chair can be, no? So things, even just because I don't have video support, no? So I can be in this way, it's always me, right? And what happens is that you, even you, but you have seen me 2 times, can easily probably recognize me, even from a small body map, no? We will see later some example of this. So you really, humans are very good at recognizing not only faces, but even the silhouette, the way of walking. I did before the example, this is Asimov walking, right? Or is a fully actuated robot walking. Why? We walk in a different way. No? It's this control. What we really believe is that this is an important aspect of a situation. And also this fact of understanding that a chair is a chair, you can solve the usual way. So I have some data structure which represent the characteristic of a chair, and I have my picture, meaning a matrix of points, and I try to compare. The limit is that, say, no, this is a blue chair. Or, hey, this is still a chair, it's a very high one. Or these chairs are different from the other ones. No? So what you do like an example of Dennett. So you add another chair, and then another chair. And then you manage the fact that some chairs, something that can resemble a chair, is not a chair. And you usually don't manage this, but this is also a chair. No? So this is what the main point about the frame of reference problem. So which I also quoted implicitly last time when I was talking about the fact that I can use chess pieces like darts. Right? I change the interpretation. This kind of thing is difficult, if you think about it, to do if you have a symbolic system behind. So AI, which has been extremely successful, I mean, Google is not only part of our everyday life, it's also one of the biggest and more successful enterprises on the planet. So AI is here, and so what we, a bit ironically, a bit friendly joking, we call the good old-fashioned artificial intelligence, it actually had many successes. Where it fails is when you have to manage symbols and you have to concatenate the symbols. So the idea that we are pushing is that these symbols, to really be useful, to be really connected to the reality, need to be emergent. This is part of a mess. So I mean, we will come back, I think, many times giving more and more details. But I think this is one of the central points. So I think that actually this is the point. No? So if you think to this model that you take the data, and here you have a data structure of a knowledge representation structure, and you can be very sophisticated on that. The problem is that this passage, in some sense, requires that you have this data structure. So the robot needs to manage the exception, and then has to deduce the possible consequence of the action. This seems good, and if you can control the environment, so if you have a semi-structured environment. So, for instance, maybe in this room, this could work. It could maybe work in a kitchen where you have a limited number of objects which actually belongs to a number of brands that you know in advance. So a fridge will be a fridge from that brand and will be a specific model. So, I mean, we live in a world which is somehow structured, and this is why a classic call it classical approach, can still work. But when we go into the wild, and this is a typical problem which is really felt in robotics, you are in trouble, no? Because I cannot list all the possible chairs, because at some point someone will say that this is a chair, and this is not in a list of chair. And okay, you add this one, no? Like in the example of R1, D1 by Dennett. Okay. And now I sit here. So, I mean, or here, no? This is also a chair. Right? I can sit here. So, actually, this is another way to see the frame of reference problem. So, another point, this is a more general nature. No? So, I think that after the two first lecture, we may have some question or some comment or some idea. So I really would take this opportunity of this technical failures, technological failures, to try to have some more, some comments, some questions, some proposal for next lecture. I would also say that this way of failing of ICT, because what we are witnessing now, I don't know about Josh. Josh was supposed to wake up at 3 or so in his time zone and give him the lecture. Maybe he got a cold, or he could not enter the university, or things like that. No? For security reasons, he was not allowed into his office, maybe. I don't know, because it's deep night in the US now. While Pedro had a network failure. So this is a significant difference, because you may think that this discussion only relates to robotics or to AI. It's something abstract. But actually, our extremely powerful, extremely successful ICT technology has not the typical characteristic, for instance, of a human brain to recover. So the network to which Pedro is connected is not able to let's say the internet is already good, but inside they are not able to find another route, pack the message in another way, reconfigure, and continue to work. This kind of intelligence is not in our technological tools. And so it's not only about robotics. This kind of embodied intelligence would help all the technology domain, including the well-established, extremely successful ICT general domain. And so this is something that, because, I mean, if you are, especially if you are a student, you should not target the technology of today. You should target the kind of technology that now we are starting to envision. So to see that there are limitations in the current approach, that really is what grounds most of the technological world today, is a way to step forward another more advanced technology. I mean, this idea of embodied intelligence is actually related. I quoted it also to understanding biological system, and what could be interesting from the application standpoint to import some biological mechanism into technological system. Because I tell, this way, the Murphy law kind of failure is typical, absolutely typical of the current level of our technology, where if you want more complex capabilities, we need more complex systems. In nature, this doesn't happen all the time. Sometimes you can have, many times you have more complex behaviors with less complexity. And now I think that despite this limitation of the current technology, we may have the possibility to listen to the wonderful talk by Pedro Lima. So we are now ending the session, and I want to do a couple of short announcements. The first is that what we have called koans. So the topics for the projects or the groups of students will be published in less than a week on October 30 on the web. Just in case you don't know what is it a koan. A koan is a typical question or story or dialogue that the Zen master poses to the apprentice, not only to check if he is progressing in Zen practice, but also to stimulate the progress. No? So this is the idea which will be behind these koans. That will be, some will be close maybe to what you may expect as an exercise or a project work that you are asked for an exam. Some are closer to serious challenge. And the idea that by overcoming the challenge, or just by trying to overcome the challenge, you will learn something. Maybe what you have listened to may be something that was not understood by us Zen masters, right? I don't think that we merit this with the service definition, but okay. So next time, the next lecture will be will continue in the thread, but will be on cognition and embodiment, and it will be broadcasted from the University of Plymouth, and will be hosted by my friend and colleague Angelo Cangelosi, and so you will also have a couple of guest lectures. So stay tuned and stay tuned on two things. Stay tuned on the koans and stay tuned on the next lecture on same hours, same time frame on October 31st. And thank you for coming. Thank you for your patience. But I think that we also learned it was a meta teaching that we received from these problems that we have by interfacing with the real world. Thank you, everybody. Thank you for coming.
Yes, thank you all for participating. I'm sorry for the technical problems, but I would like to quote a Japanese saying that Rolf is always using, Jinji o tsukushite tenmei o matsu, which means roughly, we did what we could, the rest is up to the gods. So,
exactly.
See you all next week, and remember that Europe is switching the time zone to winter time, so the time may shift for some of you. Please check the schedule that Martin sent around. So, see you next week.
Bye-bye.